weekend conference, so remember, General Conference Challenge, Monday, 3 p.m. here. Ridiculously hard questions about the Sunday morning session. So take good notes. All right, so let's go ahead and get started. We're going to talk about recurrent DNNs. By the way, sorry, this XKCD comic is not quite on topic for this. So it's getting harder and harder to find a relevant XKCD for like every topic of every lecture. But
you've been doing a great job.
the reason is actually, this is subtle, but in deep learning, you should just know this. There actually is a difference between recursive DNNs and recurrent DNNs. Those are not the same thing. So that's why this is not quite the right comic. Great, but that's with that disclaimer. First, before we get going, I'm very proud of my students. I just have to show you this. We've been working for a couple of years on a software package for deep reinforcement learning called Holodeck. And my students just released it, and I've got to play you the little video that they made. So Holodeck, what it is, you can check it out at holodeck.cs.byu.edu. So the idea is this is a simulator that you can use for reinforcement learning. You stick agents in virtual worlds. It's all based on the Unreal Engine. But the cool thing is that you can control everything from Python. So you can like step things and then tie a neural net to try to learn how to control these agents in these simulated worlds. And so I put together this video. I think I'll play for you. So because it's kind of fun, we won't watch the whole thing, but so the idea is just. You have multiple agents, like you have this little drone-like agent, and you have this like Android agent, and they can both exist in the world at the same time. There's different, there's like forests, there's multiple forests, there's like this slummy city, and you can program both of the agents, and they can like chase each other or run around. You get all these sensors, and so the whole point of this is to be able to connect up these neural nets to this. So anyway, check it out sometime. Like I said, we should probably pause it. So yeah, this is our city environment. So kind of fun. You can also like change the weather and the time of day and all that stuff. So it's a really cool project. Again, very proud of my students. Congratulations, you guys. All right. It's been like 2 years they've been working on this, so it's fantastic. Okay, so today we are talking. Last time we talked about regularization. Today. And I want you to mentally, today marks the beginning of a new section of this class. So up until now, we've been going through the basics of deep neural nets. And specifically, we've been focused a lot on images. I've talked a little bit about other, other kinds of things. We haven't really done anything with them. Well, today is the day that we leave images behind, sort of, and move on to other kinds of things that neural nets can do. So we're now going to spend the next couple of weeks talking about time and time series models. So when I say time series model, I mean models of data where the data exists in time, and that can be all sorts of things. So it could be video, so that's like images over time, but it can also be things like temperature over time, or a sequence of words in a sentence, or a sequence of sentences in a book, or a sequence of gene expression data over time, or like all sorts of things. So all those are time series models. And deep neural nets have a lot to say about how we process temporal data. But you need some special techniques in order to be able to do it. And so we now begin a discussion of what those techniques are and how they work. We'll also discuss, I think if we get there, we'll talk about why basic ideas in time series DNNs, called recurrent DNNs, don't work. The vanishing gradient problem, except now instead of gradients vanishing according to the depth of your network, gradients vanish over time. And we'll talk about solutions to that problem. And we'll introduce things called LSTMs, and we'll talk about GRUs and some other techniques for getting around it. So this lecture also is based on the blog post, which is one of your assigned readings, The Unreasonable Effectiveness of Recurrent Neural Nets. Okay, so just so that we all have the same terminology, we're going to talk about these things called recurrent neural nets. And once we have the idea of a recurrent neural net, we can solve many different kinds of learning problems. So we've been looking at things like this, where you have some input, and you go through some hidden layers, and you get some output. We're going to call that a one-to-one problem. But you can imagine that there's different kinds of things. So you might imagine that there's a one-to-many. So an example of this is image captioning. So I plug an image in here. It goes through a neural net. That neural net spits out a word and then updates itself, spits out a word, updates itself, and spits out a word. So we want to map images to captions automatically. You could also imagine many to one. So this is sentiment classification, where you have a time series of data, like maybe these are words. So a word goes into the network and it updates itself. And then the next word comes in, and those two are combined. And then the next word comes in, and the output is the sentiment. So Amazon uses this. When they look through all of the product ratings for a product, they plug them into a sentiment classifier and try to learn patterns about what sentences map to positive and negative ratings. Okay? Or maybe machine translation. So this is many to many, where we have a sequence of words coming in, and the network is processing it, and then once the input sequence stops, the network starts spitting out an output sequence. So English down here, German up here. And then there's like, various variants of this. You can sort of mix and match all of these things. Okay, so, but in every case, you have time. And by the way, some problems you can sort of formulate, you can even do time where time might not naturally be a part of the problem. So this is an example, some early work on classifying house numbers from the Google Street View house number data set. So the classification problem is I give you an image, say this one right here, and I just want you to tell me what the number is. So like Google uses this to find the numbers on houses. So one way you could do this is a one-to-one, where you take this image in, some magic neural net chugs and spits out some number between, like, I don't know, 1 and 10,000. But another way you could do it is by introducing an element of time that isn't natively there. And what I mean by that is what sometimes people do is they introduce a little attention mechanism. It's like a fovea, it's like an eyeball. And the eye sees a little subpart of the network. And the network has to look at this little subpart of the image, extract some information, and then it gets to move that eyeball around and sort of scan the image and try to determine what number it is. So that's more like, actually it's not really shown here. It'd be more like one comes in and then you have like, actually it's kind of like this, where, except it's the same image. So the network over time assimilates or aggregates all of the information about this image that it can, and then finally, at the end, spits out a number. Okay, so time can exist natively, but we can also introduce time. Okay, so what is a recurrent neural net? So here's the idea, and here's how I draw it. You have an input, and you have this thing, which we're going to call an RNN, and then there's going to be some output. And we're going to want to predict some vector of outputs. And the little arrow here means that something about the hidden layer activations inside this box depend on the hidden layer activations inside this box just at the previous time step. Okay, so more formally, we have some hidden layer activation here at time t. We've got some function, parametric function approximator, which takes as input the old activations, as well as some information from the data set. Okay, so what's tricky about this? What's tricky?
What do you use as the first old state?
Yeah, okay, so like, what is h sub 0? So what is your initial condition? Good, what else is tricky?
If you have a long sequence, you're back plugging to the beginning every time.
Yeah, okay, so right. So at time, say 100, time 100 says it depends on whatever the activations were at time 99. But time 99 depended on whatever there was at time 98. And so 100 depends on 98. But it also depends on 97. It also depends on 96. So the hidden layer activations at time 100 depend on everything before it. And so it's very difficult to train that. It's like a 100-layer neural net, except time-wise instead of depth-wise. Okay, what else is a little bit tricky about this? So it's a little bit tricky because this function, we have to be careful about tweaking this function because this function will output some hidden state, which will then help output a y, but that same hidden state is also going to affect the hidden states at the next time step. So we have to be really careful about how we set up training. I mean, we'll just use backprop, but we have to think hard about what training means when we do this. In other words, it can be tricky for this to rely on previous hidden states if we're changing hidden states around. Okay. Also notice, the parameters here don't depend on time. So the parameters of the network are reused across time. In other words, every time step, the parameters are the same. The only thing that's changing is that we're cascading the hidden unit activations in. Okay, so like here's a very simple example, simple hidden layer. So we have some input. This is what we were just showing. So we can maybe make this a little bit more concrete. How exactly can you depend both on the image and on the previous hidden layer activations? Well, maybe it looks something like this. Hidden layer activations at time t, some nonlinear thing, tanh maybe, and you have a weight matrix. So you just take your input vector, multiply it by some weight matrix, take your previous hidden layer, multiply it by some weight matrix, add them together, and then throw in a nonlinearity. So this would be a very simple dependence where HT depends both on previous input and previous activations. But we're going to imagine much more complex versions of this. Okay, so let me give you some examples. So a very simple character level sequence model, which you will implement for your next lab, might look like the following. So we can imagine that we have a little vocabulary of 4 letters, and we'll do one hot encoding for those. So our input data, maybe we'll have an input sentence like H-E-L-L-O, hello. So our first, I'm sorry, this is not my slide. I didn't even think about that until you tried that. So you can imagine that the first thing comes in, it's like some one hot encoding of that. It's going to go through some hidden layer. That's going to give us some vector. That thing's going to go to the next, etc. Okay, and then there's going to be some outputs. And the outputs we'll interpret as just regular softmax log probabilities over the next character. So in this model, you always want to predict the next character in the sequence. So I show you an H, you want to predict an E. So we want the E number here to be as high as possible. And then I give you an E, and you want the L number to be as high as possible, etc. Okay, so you've seen 0 to t minus 1 characters, and you want to predict the teeth, the next character in the sequence. Okay? So this is a very simple model that is unreasonably effective. So what you can imagine is you can imagine taking some text, and you can imagine plugging it into a model like this, and you can imagine spitting out, you can imagine trying to learn to predict the next character, just one character at a time. And furthermore, notice that we can actually sample new text. So how would we do that? Let's imagine that I show you 10 characters. How could I generate the 11th character? What do you think? Yeah, right.
You just run those 10 characters through the network and look at the output. That'll give you the 11th character.
Well, what does the output give us?
Well, the output of the 10 character will give you a prediction of the 11th character.
Right, so what specifically does it give us?
Well, distribution over.
Distribution. So how can we get the next character from that distribution?
Or take the max.
Take the max or
Treat it like
sample. Right, we could do either. Yeah. So and then we could take the sampled character as the 11th character, plug it into the network, and get the 12th character. And then we could take the 12th character, whatever we sampled or max, plug it into the network and get the 13th character. Right? So we can keep rolling this model forward ad infinitum. Okay, so very simple idea. And what is amazing is that you can actually do character level prediction of some very interesting things. So if you haven't read the blog post, I strongly encourage you to do it. I'm going to pull out some of the most amazing results from this very simple model. So here's, so imagine we have text here, sonnets by Shakespeare. Okay, data set. I give you characters, and I just want to try and predict the next character. And then I want to sample new sonnets. Okay? And see what happens. So here's what happens. So at first, when you run this character, this model, and you train it, you get this. So nothing recognizable. It looks just like a string of gibberish. Then you train some more, and then all of a sudden you start to see some structure. You start to see capitalization and maybe some quotes that make sense, and like the length of these words looks about right, and there's spaces and kind of periods where that makes sense. And then train more, and you start seeing things that look like complete, I mean, I don't know who Prince Velzomsky is, but that like looks plausible. And then you keep going, and you get stuff like this, which if you blur your eyes, looks like fully formed sonnet. But if you read it more closely, you realize it doesn't make any sense. So it says, "Why do what that day?" replied Natasha, and wishing herself, yeah, but what's amazing is that it predicts this character by character. Okay? That's what's amazing. And so something about this neural net has learned to remember that if you spit out a quote character, then the next character should probably be capital. And then you're going to spit out some stuff. And then you have to remember to close the quote. So somewhere in the neural net, it's learned, okay, the quote is open, and I'm going to spit out some quote-like looking stuff, and now I have to close the quote. And it remembers that. It learns to remember that. And that is what I think is incredible about these very simple models of recurrent DNNs. It goes deeper than this, though. So you can train it on the full works of Shakespeare, and you get this. So here is an entire play generated by a recurrent neural net. And you can see that it is constructed characters. So there's a senator, and a duke, and a lord, and a clown. And you can see that it's using Shakespearean sort of language. You can see that it's conjugating verbs, it's contracting things. You can see that it's got commas and periods in all the right places. It's using verbs and nouns properly, all of these things. But again, it doesn't make any sense, like semantically. If you try to actually read it, it's not quite there. So these guys said, all right, well, it's kind of cool that we can do this with like Shakespeare. Let's amp it up a little bit. So they said, what if we downloaded a bunch of LaTeX source code for books on algebraic geometry? And then we're going to train the recurrent neural net on that text. And we're going to have it spit out new algebraic geometry texts. And so this is what you get. So you get proofs and quotes, and you get equations, and you get lemmas, and you get like a little like I don't know QED symbol here. You get like some awesome math notation. Like it's incredible that it has learned. I don't know, kind of the impressionist version of algebraic geometry. Okay, so then these guys said, well, what if we, oh yeah, and like it even has like these figures that it decided. It's got these, like let X be a scheme, let X be a scheme covering, let this be a morphism of algebraic spaces. Like, if you just showed me that sentence, I might not know that it's nonsense. In fact, I wouldn't know that that's nonsense.
The first three sentences of Lemma 0.3 feel like the start.
It totally feels like the start of something, right?
The Z,
I mean,
integer Z is objective.
You know, it's like defining its variables. Like, of course, what's interesting is that it's redefining X here. A couple of times. So it's a scheme covering, it's math scheme. Okay, so then they said, well, what if we train it on the Linux source code? And what you get is generated C code. So this is machine generated C code. This does not compile. But you can see it doesn't use the kernel style. I don't know, maybe. So you can see it has for loops and function calls and comments. That's awesome. It's got, but what I think is amazing is it's got proper indentation and it closes its braces at the right place. So this is not pretty printed or anything like that. It actually generated the code in this way. So has to remember that, okay, I'm 2 in here, and I'm going to open another block here, and then I'm going to do some stuff, and then I have to close that block. So it's remembering things from many, many characters. And remember, this is predicting character at a time. By the way, what's extra funny about this is that every now and then it will flip into a mode where it spits out the entire text of the GPL here. So it's like, memorize that. And then it will include some pound sign includes. So where is the GPL stored exactly? It's like somewhere in the weights of the network. We don't know where, but something in the network, something in those weights have remembered very complicated, very long-term kinds of things. Okay, so hopefully you can sense the power of this. Hopefully you can sense like, oh yeah, like wow, like I had a time series problem. I might like to throw some sort of recurrent network at it and like see what I can do. Okay, so I thought it'd be interesting too to see a little bit about how the predictions work here. So this is a visualization of the state of the neural net as it's going through and doing this character level prediction. Okay, so what's being shown here is the input sequence of characters, and that's being sampled. And then below, it's showing the top 5 next characters that it thinks it's going to predict, and they're colored, shaded by probability. So darker, like more intense colors, more intense red means higher probability. So what I thought was really neat about this, so check out, let's see, so like right here, so http:// www dot something 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 something, and then dot, and then check it, and so it gets a dot here, and then check out what it thinks the next characters are going to be. COEGN. Com, or, edu, gov, net. Right? So you're like, no, it's like, that's how you tab complete something, 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 dot, something. Similarly, you can see things like, if you see a capital E and then an N, like, it's pretty darn sure that Glish is the next. Like, there's just not that many words. Similarly, it's very confident about its predictions about language, but you can also see there's times when it's far less confident. So, for example, so English language website of Israel's largest space, and then it's like, I don't know, like some word is coming next. I don't know what it is. It could be any word. So like, it's a very diffuse prediction here. Nothing is bright red. That means like it has no idea what's coming next. And that makes sense. Like I wouldn't know what word is coming next. And Sarah, you can sort of look through here and sort of see some very interesting other patterns that the network's picked up on automatically. So, tell me something. Is this an unsupervised learning paradigm or a supervised learning paradigm? What do you think? Oh yeah, I think I hear muttered versions of both. So who wants to argue for supervised? Good.
Well, you've got the training data and the labeled data in the same data set as this time series data. So you have this is a character model, so you have one character prediction and then the next character after it. So your training set is also your labels because it's time series. That's how it feels to me. I don't know.
Okay. Who says it's unsupervised? Wants to argue the unsupervised case?
I mean, essentially, you're just throwing data at it.
Yeah, so I don't think there's a right answer to this, but I want you to think about that question. It's this odd kind of thing where there's nothing called a label here. In essence, I've just given you a pile of data. I hand you all the sonnets of Shakespeare, I hand you all of the algebraic topology texts, whatever it might be. But we are somehow using that data to generate our own labels. Like there definitely is a ground truth that each character is being compared to. So it's a bit of an odd training paradigm. Okay, so let's keep talking a little bit about this. So I'd like to show now some more examples of recurrent neural net and the sort of the frameworks, the way we use them. So here's an example from machine translation. So this is German to English. Yeah, I don't actually know if that means awesome sauce in German, but that's a funny example. Anyway, so recurrent neural net for machine translation feels very similar, except that everything is a little bit bigger. So in our character level model, you can imagine that we have characters and a vocabulary over characters, and there's maybe, I don't know, a couple hundred characters if you include punctuation. Here, we use words, and so our word vocabulary is, roughly speaking, like the total number of words in the language, plus all of the variations, capitalization, possessives, things like that. So typical machine translation vocabulary sizes are on the order of 40 or 50,000. So instead of having a one-hot encoding over like 50,000, we might have over like 100, you might have a one-hot encoding over like 50,000. And these words come in, but similarly to what we saw previously, they get aggregated into these hidden vectors. More information gets aggregated, this hidden vector gets passed along until it's finally used to decode. So this guy at the very end has to somehow summarize all of the information in the entire sentence, because that's the only thing that gets handed to the decoder. By the way, this is called the sequence-to-sequence learning framework, where we have an input sequence and an output sequence. And we'll see that people, in some ways, have moved beyond this. That's actually the thing you'll code up, not for this lab, but the next lab. Okay, but let me show you a few more examples that I think are particularly interesting when people thought about this. So this is some work that was done a couple of years ago on image captioning. So the idea here is I give you an image, and I want to generate captions for that image automatically. So how can we use RNNs to do that? Well, what these folks said is they said, hey, let's take that image, let's just pass it through some pre-trained network, say the VGG network that you all now know and love. So it goes through the VGG network, and we're going to take like maybe one of the almost last layers, and we're just going to call that H0 for our RNN. And then I'm going to hand that vector to the RNN, and I'm going to sample the first word in my caption, then take that word and plug it in and update my state and sample the next word, and keep sampling until the network spits out an end token. And what's kind of amazing is, so it's like the composition of two neural nets, where you have some front-end feature extractor and then something that you learn. And this is all pre-trained. And what's like amazing about this is that it sort of works. So let's see, yeah. So what, basically just set all this, but here it is in like pictures. We use whatever this layer was. So I think this is like the almost last layer. That's right, there was actually two more layers here. We don't use those. These guys used the, third to last layer. And so they did this. They trained it on this image sentence data set called the MS-COCO data set. It's a fantastic data set. So a couple hundred, 120K images. Each one has 5 captions for it. And so you pass this image through the VGG net, grab those third to last activations, and then train your recurrent neural net to generate one of these 5 things. And here's some results. So the network generated these captions. A man in a black shirt is playing a guitar. Construction worker in orange safety vest working on road. 2 young girls are playing with a Lego toy. Well, she's young. So this one is not quite right. Boy is doing backflip on wakeboard. He's not. He is doing a backflip, sort of, maybe. But that, I think, is a trampoline on the beach. So it's not perfect. And actually, it doesn't always get things wrong, right? So a young boy pulls a baseball bat. A cat is sitting on a couch with a remote control. I mean, if you squint, that's an ugly cat. But a woman holding a teddy bear in front of a mirror. This is my favorite. A horse standing in the middle of the road. It's like, well, there's a road, and I don't see it. So it's not perfect, but I will say, in the defense of the neural net, actually it's like reasonable. So even when it does the wrong thing, it's clearly picking up on some signal. So there's no horse here, but there is a road, and there's no teddy bear here, but there is a man, there is a woman, and there's no cat here, but there is a remote control. So like it's not perfect, but it is like clearly doing something reasonable. And potentially, if you train this on more data for longer, using bigger networks, et cetera, you might be able to do even better. What I think, by the way, is remarkable about this result is, remember that they didn't retrain this. So all the information for generating captions to these has to be contained in this 4096 dimensional vector. And remember, this was not trained to do this. Like it was trained for something else entirely. But that apparently is a useful representation of the semantic content of the image at a pretty high level.
When we train this, did they allow grades to flow back through the network? Did they just fix?
So they've done both. At this point, the question was, did they allow gradients to flow back through and tune the weights of the BGG network? I believe in this particular version they did not, but people said it's happened. It's the obvious thing to do. It's like warm start these with some BGG pre-trained weights, and then fine-tune them. With what they're actually trying to get them to do. Yeah, totally. And I'm sure it improves performance as long as you don't overfit. Okay, so let's talk a little bit about vanishing gradients. So why do gradients vanish? Well, you sort of imagine if we're trying to train one of these things, and we have a bunch of inputs, we have a bunch of outputs, and those are giving us losses, and we have a bunch of states. If we want to update something about the weights and how the error signal from time point 4 affects our weights, remember that this error is affected by this hidden state and the weights that generated it. But this hidden state is affected by this hidden state and the weights, et cetera, all the way back to the beginning of time. So if we want to take information from E4 and use it to tune our weights, that's going to backprop all the way through this network. Okay, so you can immediately see the problem. Here's the problem. The problem is, if you we're not going to go through this, don't worry. If you look at the gradient, say, of E3 with respect to the weights, so you'd just like to know, hey, I mispredicted this word here, so I want to tweak my weights to improve my prediction on this word. Problem is that you have these gradients that flow all the way backwards, and you get this product of gradients, and you have terms that look like this, where you have the product of everything up until then, of how the states were affecting each other, and then how these things were affecting the weights. And things like these products, we've sort of seen, if you multiply a bunch of things that aren't one together, they go to 0, or they go really big, really fast. And so the problem is this product of gradient terms. So by the way, this is called backprop through time, where we take a network and we unroll it a fixed number of time steps, and then we just try to train that unrolled network. And it's a technique that was one of the earliest techniques for training neural nets, has since been discontinued in favor of more advanced techniques. And that's what I'd like to talk about right now. So LSTMs are now kind of the new standard, which actually has just recently been supplanted by another new standard, but this is still really good for you to know. A lot of people still use these. So LSTMs. So this was first proposed back almost 20 years ago, so back in 1997. So it stands for long short-term memories. And the idea of an LSTM is the following. It says, recurrent neural nets and these networks that are unfolded over time, and we try to train them, like, that's cool and all, but if the network learns to remember something, it's not because we forced it to learn to remember. It sort of had to do that on its own. And if we know that we want the network to be able to remember things, let's set up the topology of the network in a very specific way so that it's easy for it to remember things that it needs to remember. And hopefully, we'll also be able to construct it in a way that makes gradients flow cleanly through it so that the gradients don't explode or vanish. And so the big ideas are that a neural net in time needs to be able to do a couple of things. It needs to be able to transmit information to the future. So you want it to sort of look like an identity. Like whatever it's remembered from the past, it wants to be able to still remember in the future. Except that every now and then you want to remember something new as a result of your input. And you might also decide that you want to forget something. So you want to be able to learn when to remember things. You want to learn when to forget things. And you want to learn when to just pass things through in an unmodified way. And so LSTMs are a specifically, thoughtfully designed architecture to help us do that. And here it is. Here's like, so I think that there's actually a picture that does a much better job of helping us understand this. So here's the picture. Okay, so this is the sort of the canonical figure for an LSTM block. And let me unpack this for you. So X's are your inputs. So think images or words or whatever your time series is over. They come in here and lots of things happen. But you can sort of imagine that this block has a couple of inputs and then has this output here. So we'll ignore this output for just a second. And we'll just look at this path. So the first thing to notice, so C and H are, roughly speaking, the state of the LSTM. This is the thing that gets remembered and gets passed through. The C is what I think of as the true state of the LSTM. And so you can see that the C thing here, whatever the previous C was, goes through, gets multiplied by something, gets added to something, and then just gets passed right through. And this is the forget bit, and this is the remember bit. So we think of, imagine that this is some vector of information. And as it's going through this block, when we multiply it by things, we're going to multiply by either 1 or 0. So if we multiply by 1, we remember it. If we multiply by 0, we forget it. Then we're going to add something, and we're going to add in things, and we're going to mask where we want to add them in. So we'll decide which entries in this vector we want to modify, and then we'll selectively enter information into those vectors, and then we'll pass it on to the next guy. And so notice that if we multiply by all 1s, what happens? Like nothing. So we can learn to just pass information through. And if we add all 0s, what happens? Nothing. And so this thing passes unmodified through this, can pass unmodified for as long as we need it to. Okay, so how do we figure out, let's look at forgetting first of all. So let's just forget about the orange path for a second. So what happens? Information comes in here, and it goes through a sigmoid gate. By the way, there's weights that are not shown here. But like we take this, multiply it by some weight matrix, and then goes through a sigmoid. What does a sigmoid do?
0 to 1.
Yeah, squashes it to 0 to 1. So the output of this thing is going to be either, well, it's going to be something between 0 and 1, always. So this is one of the few places where it's like okay to use a sigmoid. Because you really want this to actually be between 0 and 1. So if the sigmoid output's a 0, we're going to forget something. If the sigmoid output's a 1, we're going to not forget it. We're going to remember it. So what else gets fed into this sigmoid? Well, it depends on whatever input comes in. It also depends on whatever we remembered previously. So this little bit right here is going to learn what to forget as a function of things that it's currently seeing and things that it's remembered in the past. Okay, so any questions about that so far? Let's talk about this. Yeah.
Is the remembering forgetting, is that binary, or is it like, is there a sliding scale?
Yeah, so it's not exactly binary because the sigmoid can output things that are between 0 and 1. But I'm just saying, like, I think it's useful to consider the sort of extreme behavior. And so in practice, it could learn to multiply things by 0.5 into 1. Okay? What else you got? Ask me some questions about this. Yeah, go ahead.
Are you going to get to what the pentagon is? Is there a word in there? Or the little...
Yeah, that's tan H.
Okay, thanks.
Welcome.
Does this imply that the cell state is the same size as the output?
So the cell, okay, yeah, sorry. So the cell state, the thing to remember, is not the same size as the output. So the output is this thing here.
Yeah, but it's just element-wise operations all the way from the state to the output.
Well, this goes, yeah.
Typically, you would have weights that you multiply.
Yeah, I think right here, you actually have a weight matrix before that 10H.
Okay.
And that will change the size of the state to match the size of the output. Yeah, sorry, that's not clear, but everywhere where there's one of these symbols, it means weights plus nonlinearity. Yeah, that's a little clearer here. So you can actually see that the output HT, which actually isn't shown here. Oh, shoot, I guess I forgot that. Yeah. Wow, anyway, you can see that everywhere where there's a nonlinearity, there's always these weight matrices that sort of map things to the right dimension.
Okay.
So similarly here, your input and your C are not necessarily the same size. This thing has a weight matrix